All right, so let's chat about this first derivative test. As we noted, if a function switches from either increasing to decreasing or from decreasing to increasing, we would have to have at some point come across a local or relative max or min. And so that's what we have here. We have the types of extrema followed by like what is happening, right? So when we go from negative, oops, that's not red. We go from negative to positive in terms of our slope of our tangent line of our first derivative, right? We're going to have a minimum. Boom. And if we move from positive to negative, we will have a local maximum. So that's what we're going to be doing. There's a process here. Basically, the process is exactly the same as what we did to find our intervals of increasing and decreasing. Got to find those critical values, throw them on a number line, make a plus minus table, and then we can see if there are changes from positive to negative in our plus minus table, indicating that we have a relative or local extrema. So let's go ahead and see one example. So again, we get our good friend, the polynomial. It's scary at first because there are some fractions, but we can see once the power rule comes into play, those fractions are going to go away. And we're looking for relative extrema, giving reasons for our answers. So let's go ahead and sort of follow those steps. We know this is all about the first derivative and the first derivative test. So it looks like we have a negative x squared plus 3x plus 10 for our derivative. Okay, so we know we need to figure out what our critical values are, our critical points. These are the spaces where my graph could potentially change sign and therefore show that we have a relative extrema. So our critical values, don't have to worry about this not being an undetermined value because it's a polynomial, it's smooth and continuous. So we will just say, well, when is this thing equal to 0? Oops, I almost lost a sign there. I'm going to go ahead and multiply everything by negative because I don't like the negative leading coefficient. I'm going to factor because typically things work out factorably in calculus. It's just the magic of being in a math class. Otherwise, you would have had to use either completing the square or the quadratic formula. So it looks like we get out solutions of x is equal to 5 and x is equal to negative 2 for our critical values. All that's going to do is inform my plus minus number line, right? So we're going to go ahead, make ourselves a number line, negative 2 up to 5. We know these are our possible relative extrema, negative 2 and 5. And we can go ahead and do however we want. We can use test points. I'm going to use the shape of our original f prime of x here. We know that's a downward facing parabola, so it's going to do a little of that action. So it's going to be negative, then positive, and then negative. Now, don't get confused by what's happening to our first derivative. We care about what's happening to the original function, right? We're looking for relative extrema on that original function, f of x. So let's just sort of sketch what's happening. If we're thinking about f of x, I'll just go ahead and give myself like an actual thing. We don't need, like, I'm going to be really silly and not put this thing in anywhere that makes sense. We do know some stuff, right? We see a negative leading coefficient, odd degree. But what really matters is we must be decreasing. Here, let me get myself negative 2 and 5 on here so that I can actually have some spots that are doing. So my function is, I want to use this, probably nothing like this, but it decreases. That's that negative portion, right? This section is decreasing until I get to negative 2, and then it's going to become an increasing function. Oh. Oh, and then once we get all the way to 5, this thing is going to decrease again. So we could say, what was it? Okay. There is a relative minimum at x is equal to negative 2. And it says explain the reason because, I just want to like point to my beautiful graph above, f prime switches from negative to positive there, and a relative maximum at x is equal to positive 5. Oh, I just realized my plus didn't actually work because same reason except for dot, 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 plus 2 minus. All right, let's go ahead and pull up Desmos just quickly to verify what we're seeing. I hope I still have my Desmos open. I do. All right, so I'm going to bring this back. I'm going to type in our new function, which is negative 1/3 x cubed plus 3/2 x squared plus 10x plus 3. So you'll notice my drawing is probably atrocious. There you go. Yep. But there we go. We can see that smallest point is at negative 2, and that value is a negative 8.333 if we needed it. And our highest point happens at, not highest point, but our local maximum happens at 5 with a 48.833. So that was the original graph that we were looking at, and that's using the first derivative test.